Welcome. We are Wolf Technical Services, and we're excited to talk to you today about our work developing the next generation of rotor wing technology, individual blade control. Wolf Technical Services is a small business located in Fishers, Indiana. We are a multidisciplinary engineering firm that develops and designs products for defense, consumer, and medical industries. The company started in 1977 as a forensic engineering firm, performing accident reconstruction and product failure analysis. In 2005, we worked on our first SBIR focused on a crash safety system. Since then, we have completed 27 additional SBIR development projects for the U.S. government, including 10 Phase 2 SBIRs, as well as several Phase 2 enhancement contracts. Outside of the SBIR ecosystem, Wolf Technical has experience as a prime contractor for the U.S. Navy and Australian Army. The company commercialization index is 70%. Our in-house engineering staff covers a wide range of engineering disciplines. Our principal investigators specialize primarily in mechanical, electromechanical, biomedical, and optical design engineering, but we also have experience in robotics, control systems, instrumentation, and test equipment design. The underlying mechanical issue is that helicopter rotor control mechanisms have not changed significantly in over 30 years. Traditional controls move all rotor blades simultaneously to control pitch, pitch angle, and altitude. We believe that advanced control systems have developed to the point where they can begin to replace legacy rotor control mechanisms to improve performance in rotary wing aircraft. Challenges of practical implementation of the existing technologies include reliability, lack of redundancy, failure modes, system performance, packaging, production, cost, and maintainability. NASA started experimenting with different control mechanisms in the early 1990s, including one promising approach, individual blade control, which we will refer to hereafter as IBC. As IBC technology has improved since then, Army and Navy technical leads have shown interest in further development for their rotary wing platforms. However, even with Armed Services investment, existing IBC technology has only been implemented in experimental settings, with actuators placed in the rotating system in series with a conventional swash plate mechanism. Utilizing these actuators in the rotating portion requires hydraulic and electric slip rings, which contributes to increased technical complexity and risk. The benefits of IBC are well established: better handling, reduced vibration, lower noise, and longer component life. But practical implementation has been limited by reliability, complexity, and integration challenges, especially with systems that require rotating actuators and slip rings to transfer power between the stationary and rotating portions of the rotor system. The Navy's challenge is to enable fully independent control of each rotor blade, not just at the primary frequency, but up to 7 times that frequency, while maintaining extreme reliability with a probability of loss of control, P-lock, of less than 1 in 100 million flight hours. Maximum pitch authority also needs to remain comparable to existing platforms. This applies to both traditional helicopters and emerging eVTOL aircraft. Wolf Technical Services has developed a novel architecture that places actuators in the stationary frame, avoiding many of the failure points of past designs. Blade pitch is transmitted via a mechanical linkage. The primary performance requirements for the system are blade pitch authorities of plus or minus 15 degrees at the primary frequency, plus or minus 2 degrees at 2 times the primary rotor frequency, and plus or minus 1 degree at 7 times the primary rotor frequency. The system must also work with rotor systems operating at 200 to 600 revolutions per minute and scalable up to 8-bladed systems. Recall the high standards set for us. Reliability targets are for a minimum of dual redundancy on actuators for each blade and P-lock of less than 1 in 100 million flight hours. The system must also be resistant to environmental conditions tested against MIL Standard 810 standards. Lab demonstrations and testing on a small-scale prototype system were completed during the Phase 1 and initial Phase 2 efforts. validating core actuation and mechanical power transmission concepts as well as performance. Ground testing on a higher fidelity full scale prototype is planned for completion by the end of the Phase 2 period in Q3 of 2027. This system will incorporate additional features addressing reliability and environmental resistance aspects of the system design. One of the biggest differentiators is our use of actuators in the stationary frame. Unlike legacy IBC systems that place actuators in the rotor hub, where they're subject to high centrifugal loads and harsh environments, our design transmits control mechanically from the fixed frame to the rotating blades. This dramatically improves system reliability and maintainability, and eliminates the need for high-speed data or power transfer across a rotating interface. The system supports higher harmonic pitch inputs, up to 7 times the primary rotor frequency. That enables fine control over aerodynamic loads, leading to significant reductions in vibration and acoustic signature. For military platforms, that translates to stealth and survivability. For commercial use, it's about noise abatement and ride comfort. One of the key advantages of our design is that it supports multiple actuator types, including electric, hydraulic, and electro-hydraulic actuators. This makes the system highly adaptable for integration across different aircraft platforms, depending on available onboard power, environmental requirements, and mission needs. To control the rotating blades from a stationary actuator, we developed mechanical power transfer mechanism. This approach preserves the benefits of a fixed frame actuator while drawing on proven concepts from legacy rotor system designs. The system design is also conducive to dual or triple actuator redundancy for each blade to improve reliability. Feedback sensors for control are also located in the stationary frame to eliminate the need for complex slip rings. Our current program is focused on demonstrating and validating the key performance capabilities of the IBC system in a grounded lab environment. That includes proving out the actuation system, control authority, and harmonic response under controlled conditions. The next step will involve higher fidelity ground testing, such as whirl stand evaluations or testing on grounded rotorcraft platforms to simulate operational loading and dynamic behavior more realistically. These efforts are planned for post-Phase 2 activities. Ultimately, transitioning to flight test and fleet integration will depend on strong collaboration with rotorcraft OEMs and continued support from the Navy. Those partnerships will be essential to refine the design for airworthiness, integrate with specific rotorcraft architectures, and move toward production deployment. The benefits of IBC include reduced vibration, improved performance, and lower acoustic signature, all of which are highly attractive across the rotorcraft industry. In the military sector, IBC can enhance mission effectiveness by improving handling, extending component life, and reducing noise signatures. On the commercial side, ride quality and noise reduction are key differentiators, especially in densely populated environments or for urban air mobility. IBC's ability to address those factors gives it strong potential in these sectors. Because the core system is platform agnostic and scalable across blade count, rotor speed, and actuator type, it can be adapted to a wide range of platforms including conventional helicopters and eVTOLs. IBC technology implementation has value for both legacy fleets and next-generation rotorcraft. Our commercialization strategy is to license a platform-agnostic version of this technology with strong IP protection. Lockheed Martin's Sikorsky subsidiary is our current transition partner, and we're open to additional OEM partnerships to expand integration pathways. Importantly, to reduce risk for technology development, we have conducted extensive risk mitigation for partners, including system integration, size and weight, reliability, actuator power and speed, and sensor signal transmission across stationary and rotary frame surfaces. Give us a call to discuss how we can conduct the same assessment for your platform. Thanks for your time. If you'd like to discuss the technical details or collaboration opportunities further, please reach out and we would be happy to connect.